Okay, in this video, we're going to consider developing this algorithm and circuit that we're going to use to convert binary to BCD. So we're going to start with a 7-bit case, and I'm going to let you extend this to a 10-bit case. All right, so here's the idea. Let's start with 7 bits and let's do the double dabble on the biggest number that you can represent in 7 bits. So that's all ones, okay? So 7 bits with all ones, the biggest number you can represent would be 127 in decimal. All right, so let's go through the algorithm and see how that works. All right, so first of all, double. And so we double by shifting. Okay, there's only a 1 in the ones column, and so we don't need to dabble. So we shift again. There's a 3. You don't need to dabble because you can't possibly be more than 5 or more because you only have 2 bits. All right. So the first 2 shifts, we didn't need to dabble. The third one, though, we have a 7 shifted in here. Let's go ahead and shift everything else over. And then we realize we have to dabble that. 7 plus 3 is 10, so we write 10 here. All right, now let's shift again. Okay, so when we do the shift, the 10's place is okay because that's just a 1. And then the 1's place, we see a 5. 5 means we have to dabble. 5 plus 3 is 8. So we replace 5 with 8. Shift again. All right, I see a 3 in the 10's column and then a 1 in the 1's column. I don't need to dabble either one of those. So shift again. Okay, so in the 10's column, I see a 6. And so I need to dabble that. 6 plus 3 is 9. All right, so that will force the right carry coming into the hundreds place. Okay, and then on the very last step, we do not need to dabble. All right, so we'll draw a line here indicating this is the last step where we're shifting the last bit in. Okay, so when I do the shift, 1, 0, 0, 1, 0, and then 0, 0, 1, 1, 1. Okay, and so does this match what we expect? Well, in the hundreds place, I'm seeing a 1. And then in the tens place, I see the 2. And then in the ones place, I see BCD 7. All right, so that's doing the right conversion for us. All right, so the reason I set that up is that we want to come up with the algorithm to make this happen using the dabble circuitry that we had talked about in the previous video. So what we can do then is mark all the places where we could potentially need to dabble. So I'm seeing these 4 places here. The bit pattern could end up being 5 or more, and so I would need to dabble. All right. And then this in the tens place, the first 2 entries that show up here and here aren't 3 bits wide, so I wouldn't need to dabble because they couldn't possibly be 5 or more. All right, so those are the dabble registers or dabble 4-bit patterns that I need to identify for my circuit. All right, so the next thing I'm going to do is I'm going to draw some. I'm going to indicate the data positions. So this is 7 bits of data. So let's call this 0, 1, 2, 3, 4, 5, 6, 7. And then you'll see I'm going to have to extend this a little bit, but I'll get there when I get there. All right, so what I'm going to do next is I'm going to mark from this 0 column, okay, let's see. Oh, it's 7 bits of data, so 6 through 0. All right, so I'm going to mark from this column all the way down, carefully lining these up. And this shows me the direction of the bit flow. Okay, so keeping those going in this direction like this. I can mark these off. And you notice there's nothing here, so let me fix that in a second. So this would be, you put in a leading 0. Because we know this BCD conversion expands the bit width, from binary to a less efficient representation. It's BCD that takes more bits. Okay, so that gets expanded, and then the next position over does too. All right, so put this like that. All right, so this identifies this pattern. And what I'm going to do now is I'm going to rearrange this to where all the data bits are in a vertical configuration instead of a horizontal configuration. So I'm just going to show you the answer here. So what I did here was I shifted the bits over, right? Each one of these, instead of being on a diagonal, if I shifted everything up, all these blue rectangle boxes would be shifted in their alignment to look like this. Okay, and so this is the schematic diagram that I want to use, where each one of these is a dabble block, where you do the add 3, conditional add 3. All right, and so from there we can start to instantiate circuitry to do the binary to BCD conversion. All right, so what I would need is a module for each of these blue rectangles, and that's going to be an add 3 module. And then I need a scheme for connecting the wires. All right, so what my recommendation would be is that you make wires that are 4 bits wide, because each of these dabble components is 4 bits wide, okay? And I would make X0, X1, X2. I told you to make them 4 bits wide, but I didn't do it. So let me scoot that over. 3 down to 0. And I have some wires for each of the inputs, 0 through 4. We're going to have 4 of these rectangular blocks. Okay, then I do the same thing for each of the outputs. I skipped X2. Okay, and then I instantiate the add 3 modules. All right, so C0. All right. All right, so C0 would have X0 coming in and Y0 coming out. C1 would have X1 coming in, Y1 coming out, and so forth and so on until you get all these modules instantiated. All right, but then I have to take a look and say what gets connected to the inputs. All right, so I have to assign these wires on the input side. The output sides are easy. Okay, so they sort of come by default. All right, so I'm going to assign X0. And I look at my diagram, and I see that on C0, I have a 0 coming into the first bit, right here, right? This comes down. Let me change the color and the width. So this comes down. That's a 0. So I'm going to put 1 be 0. And then I take a look, and what I have next is the data lines coming in 6 through 4. So 6 through 4 comes down from the data lines. Okay, so what I would put down here for the assignment, if D represents the data, bits 6 through 4 are what connect to the input of C0, which we call X0. All right, then I need to do the same thing for X1, but I get that. That's the whole point of this diagram. I get that from the diagram. Okay, so from X1, what I'm seeing, let me change colors for this different layer. I see C0 from 2, I'm sorry, from 2 down to 1. Remember, it's 3, 2, 1, 0. Okay, and then in the last position of C1, I have D3. Okay, so I can write that down. All right, so I know I have not D. I have the output of 0 from 2 down to 1. I'm sorry, 2 down to 0. That's why I was confused. Wasn't enough wires there. So 2 down to 0 is 3 wires. Okay, so you see the input here, 2, 1, 0, are the outputs of C0. All right, I think you're following me. And then the input is D3. So my task here is to continue this process and assign all the inputs for X3, X2. X3 and X4 till I get all the inputs assigned. All right? The outputs get assigned through the add 3 modules. So X0 comes in, Y0 comes right back out. And then finally, I need to look at the diagram. So I'll send you the test bench for this 7-bit case. But finally, I need to look at the diagram and assign the outputs. Okay, so I look at the outputs, for example, for the ones. The ones are C to 1, C, the output for C3, so it's Y3, 2 through 0. And then I have, looking at the diagram, I have D0 showing up as the last input to that output assignment. All right, so then you need to do the same thing for tens and hundreds. All right, so that gives you the idea. You can see how you'd write the Verilog code. I'll include a test bench. One of the other things you need to do is come up with code for the add 3 module. So I'll cover that in a separate video.